good morning or good afternoon, depending on where you are. So today is our great pleasure to have Dr. Chu Xu speaking with us. So Dr. Chu got his graduated from Beijing University in 2009 from his with a bachelor's degree, and then he went to Yale University for his PhD. After got his PhD in 2015, he moved to Rice University for postdoctoral research position before he started as assistant professor at Toronto University. So Dr. Chu's interest mainly focused on the rock records of the orogenic dynamics and the geochemical processes in the lithosphere. So today he's going to talk about the topic that as he has shown in the slide. So with that, I will give the rest of time to Dr. Chu, and we have about like 44 to 5 minutes for the presentation, and then we will interact with the audience for about 15 to 20 minutes. So with that, it's your time.
All right. Thank you, Professor Gang. Good morning, good afternoon, good evening. My topic is about the Grenville Plateau. In this talk, I will compare the Grenville with Tibet, and we want to explore the tectonic and the implications on the surface evolutions. Before I start the topic, I want to acknowledge that these works are Adam and Winnie's undergraduate and master's thesis, and they are under review. The projects were carried out with the collaboration with researchers from Peking University, State University of New York, and the Chinese Academy of Sciences. The work is supported by NSERC, Common Fund, and NISFC. So the Grenville province is on the east margin of North America, or known as Laurentia. The Grenville province extends thousands of kilometers from Ontario to Newfoundland. This province, the Grenville province, was the core of the supercontinent Rodinia. It further extends north to the Swaconavian belt in Baltica. In the United States side, there are a few Grenvillian inliers that extend from Vermont all the way to Texas. Let me switch to pointer. Okay. So this is a huge orogenic belt. It has been, it was active for hundreds of millions of years. There were several organic cycles known as Aldervian, Shuangyan, Alt1, and Virgulate. The strictly defined Grenville origin includes the Alt1 phase and the Virgulate phase. According to the model ages and the neodymium isotope systematics, we know that the Grenville province and the inliers, the Hudson Highland Massif, Berkshire Massif, and the Green Mountain Massif are broadly of Laurentian affinity. The southern inliers have Gondwana affinity. So there is the hypothesized Grenvillian suture, or Alt1 suture, that locates somewhere between Maryland and Virginia. The Grenville province is in many ways similar to the Himalaya Tibet origin. So when the Indian plate collided with Eurasia, there were a few small twins trapped between the two large continental masses. They are Lhasa, Changtang, and Changpanganzi. These twins are broadly Gondwana twins, and this is the Yagudambu suture. And the Himalayan origin here is bordered to the Indian plate by the main boundary thrust. Okay, I will not go to the details of this orogenic process. Very similar in the Grenville. So this is Amazonia, and this side is Laurentia. Before the two large continents collided, there were a few smaller continental blocks. Okay, that gave rise to these orogenic cycles. The Alzervian orogeny is featured by the collision between Laurentia and Alzervier island arc. And Schwangen is basically following this collision, and the Schwangen is featured by a widespread crusto and mantle-derived magmatism on the Laurentian margin. And finally, there was this Alt-1 regolith phase, which was characterized by the final collision and culmination of this continental collision. So both Tibet and Grenville were protracted large origins. But Grenville is unique in many ways. First of all, the Grenvillian magmatism is characterized by this AMCG suite. They stand for andesite, like this andesite, mangerite, charnocite, and granite. Mangerite is OPX-bearing monazite, charnocite is the OPX-bearing granitoid, and there are massive granitoid intrusions that are A-type anhydrous and within plate geochemical features. So they are widespread in the Grenville province as well as in the Adirondacks. The metamorphic grade of the Grenville province is extremely high. The granulite facies trends extend all the way from southern Ontario to Quebec, through Quebec to Newfoundland. So this is about 2,000 kilometer long granulite facies trends, and there are a few high pressure granulite or high temperature aggregates. So both metamorphism and magmatism show that this origin was protracted, very massive, and it's a hot origin. According to the geochemical proxies, the Grenville province, or more broadly, the assembly of Rodinia, was particularly hot. This is the compilation published by Liu et al. In 2017. Here, a panel shows the zirconium concentrations in plutons, and this is the neodymium, niobium concentrations in the plutons. And the peak of zirconium as well as the niobium are quite apparent during the assembly of Rodinia, showing a high temperature geochemical feature. The geochemical compilation of the Grenvillian or Rodinian plutons plot within this intraplate in this diagram, and also intraplate here. So actually, although this is the organic magmatism, the geochemical features of the magmatism is characterized by within plate features. Okay. Although there are also these typical arc magmatism. So we can infer from this pattern that during the assembly of Rodinia, there was a lot of involvement of the mantle-derived magmas. And here is a compilation of metamorphic pressure temperature gradient by Holder et al. 2019. So from Archean to the Cenozoic, the so-called the paired metamorphism becomes more and more apparent. So this is the peak of low temperature, high pressure metamorphism. This is the peak of high temperature, low pressure metamorphism. And we note here during the assembly of Rodinia between 1.4 to 2.9 billion years ago, this high temperature peak is even hotter than the high temperature metamorphism in Archean and in early Proterozoic. So again, both the metamorphic records and the magmatic records show that the assembly of Rodinia was particularly hot. The Rodinia assembly is quite distinct compared with other supercontinents in that the Rodinian origins were very thin in the terms of active continental crust. This is a compilation published by Tang et al. In this year. Here is the frequency of inferred crustal thickness, and the x-axis is the crustal thickness, and you can see here the Grenvillian origins are in general thinner than the North America Cordillera and the Cenozoic southern Tibet. So we hypothesize that the hot origin is in some way associated with the thin crust. So if the origin was particularly hot, then the overthickened crust is rheologically weak, so there should be repeated gravitational collapse during the orogeny. From the bottom of this crust, the thermal erosion and the delamination introduced by the hot mantle would also thin the crust, and the involvement of a hot atmosphere should give rise to repeated rifting, the extension during the origins, during the orogenies. Okay. Then you might have this question, how we calculated this crustal thickness. Okay, that was based on a few geochemical proxies. So this is the mantle melt partition, mineral melt partition coefficients of these minerals, and the x-axis is the rare earth elements from lanthanum to lutetium. Okay. Garnet is featured by enrichment of heavy earths and depletion in the light rare earths like lanthanum. Clinoparexin and amphibole have the similar trend, but the enrichment of the heavy rare earths is not as pronounced as the garnet. Based on these partition coefficient relationships, Profeta et al. In 2015 proposed this proxy for the crustal thickness, or the depth of magma fractionation to the lanthanum ytterbium ratio, N here stands for normalized to the concrete. In the granitic magma, fractionation of garnet and amphibole play an important role, as well as the plateau clays. So if the magma, the source region of the magma was at a high pressure environment, then there should be enhanced amphibole and garnet fractionation relative to the plateau clays, because when the pressure is high, garnet and amphibole are more stable than plateau clays. Okay. So a lot of heavy rare earths is sequestered by these restite in garnet and amphibole, which leads to the increased ratio of lanthanum over ytterbium. So this is the rationale behind this equation. With higher ratio is less than ytterbium, the general depth of fractionation is greater. So then if we assume that the fractionation took place at the base of a crust, we can just correlate this depth of fractionation to the thickness of the crust. And of course, we ignore these minor effects of simulation and or magma mixing. So to apply this geochemical proxy, we need to compile a large geochemical data so that these second order factors cancel out. This is the geochemical proxy based on the bulk rock chemistry. And in a recent publication by Tang et al. 2021, he proposed another geochemical proxy on the basis of detrital zircons, okay, based on the ratio of europium and europium anomaly. Here, this europium anomaly or this europium star is the geometric mean of samarium and gadolinium. The relationship is here. Okay, so when this europium anomaly is more pronounced, the depth is greater, because this europium over europium star in magma denotes the presence of plagioclase. Unlike other rare earth elements, which are trivalent, europium can be either bivalent, divalent, or trivalent. When this is europium 2+, it is particularly compatible with plagioclase. This is the peak of plagioclase. So when plagioclase is present in the restite, where pressure is not that high, the magma coexisting with this plagioclase restite is depleted in europium. Right. Another factor that controls this europium over europium star is the redox. At a greater depth where garnet is present, garnet preferentially sequesters Fe2 over Fe3, which leads to a general oxidation of the system. Okay. And in that case, the ratio of europium 3+ over europium 2+ is greater, so that in general, europium is less compatible with plagioclase. Okay. Then the europium over europium star in zircon is sensitive or almost linear to the europium over europium star in magma, so that we can just use the europium star ratio in the zircon to represent the europium anomaly in the magma, which is in turn associated with the phase relationship, and the phase relationship is controlled by the pressure. Okay, and then with the similar assumptions, we can just correlate this to the depth of to the thickness of the crust. Here, I want to note that the europium anomaly proxy was calibrated against lanthanum over ytterbium. So in theory, there should be no systematic discrepancy between those proxies, and any differences in the derived crustal thickness should come from sampling bias. To make this assumption robust, we have to remove the zircons from the ice-type granites, because the fractionation of ice-type granite might not take place at the bottom of the crust, so that the pressure does not represent the thickness of the crust. In a paper by Zhu et al. 2020, she proposed that the phosphorus content could be a good proxy to discriminate S-type granite from I-type granite, because the phosphorus is in general concentrated in the zircons derived from S-type granites. The motivations of the projects are fourfold. First one, we want to do a field-based benchmark to test the feasibility and the validity of investing organic dynamics via detrital zircons. Basically, we want to compare these two geochemical proxies. Then we explore the temporal evolution of crustal thickness to understand or to elucidate the knowledge regarding the Grenvillian orogenies and plateau formation. Then we did a petrologic case study to test the inferred tectonic framework. And finally, we want to discuss the implications on the tectonic surface evolution in the Mesoproterozoic. We compare the published geochronology and the geochemical data of the Grenvillian protons, the broadly defined Grenvillian protons with the age 1300 to 950 million years ago. We collected the sources from the provincial or state survey reports. Most of these reports are available on the dataset of Canadian Geological Survey or USGS. Okay. We also put in these geochemical geochron data published in papers and other datasets. We only include the I-type and A-type granitoids with a silicon content ranging from 55% to 75% weight percent. There are 124 plutons that extend from the Blue Ridge through Maryland, New Jersey, New England, Adirondacks, Ontario, Quebec, Newfoundland. There's one inlier in Nova Scotia. Here we differentiate the AMC plutons from the normal granitoid plutons, and we also compare these plutons to the south of this inferred Altman suture, because these are broadly Gondwanan rings. These plutons are broadly intermediate to felsic in composition, plot here, and they are mostly metaluminous I-type granites. There are a few per-alkaline and per-aluminous plutons. In addition to the bulk rock chemistry compiled based on the published data, Adam Brudner last summer did this field trip to Ottawa River. He just collected the river sand at a series of localities. Then we picked the zircons and we run the dating and the trace element determination on LA laser ablation ICP-MS. We removed the data with enrichment of phosphorus to remove the zircons derived from S-type granites. Remove these metamorphic zircons based on the thorium-uranium ratio, and we remove the zircons with high light rares concentrations to avoid the compromise by the inclusions. So here are these sample localities from Mantua to Ottawa along this Ottawa River. And in this panel, it shows the drainage basin of the Ottawa River. The Grenville front is about here, and this is the taxon boundary. So at number 1, where it is closer to the Grenvillian front, there are a lot of Archean zircons derived from the Canadian shield. And this is the magmatism, magmas in place during the assembly of Nuna, the previous supercontinent. and there is the pronounced peak at about 1.4, which is regarded as the protolith of this metamorphic trend. And to the south, where we enter this metasedimentary belt, the Grenville age plutons dominates. All right, and we just plot these RE patterns of all the zircons here, except for a few outliers. These zircon patterns are just normal patterns for zircons derived from granitoids or intermediate rocks. So here is the results. Before I present the results, I want to say that we input 124 plutons. Okay, and on each single pluton, there could be more than one data point. So there are more than 500 data of geochemistry and geochronology. After filtering, there are 183 zircons from Ottawa River, and we add another 76 zircons from St. Lawrence River. We did the Boothstrap resembling using a plus minus 25 millimeter spin size. We calculate these moving averages generated using A-cycle software, and we discard the highest and lowest 5% in each 50 million year spin to reduce the scattering, right? And here is the trend constrained by the bulk rock geochemistry, lanthanum over ytterbium, and the green trend is constrained by the zircon data. The shaded areas stand for the organic cycles, Alzerbian, Schwangen, Alt1, and Regulate. And here it shows that at the beginning of this Schwangen and the Alt1 phase, this crust thickness was thicker than the rest of these Grenville ages. The Alzerbian thickness is about 51 plus minus 5 kilometers, followed by thinning. Okay, and then it was thickened again at early Schwangen to about 55 kilometers, followed by rapid organic collapse to thinner than 40 kilometers that are dominated by AMCG intrusions. The crustal thickness reached another peak at early Alt1 to about 70 kilometers, and there are repeated thinning throughout Alt1 and Regulate phases. On this panel, it shows the zircon crustal thickness constrained by the zircon-europium anomaly. It shows a similar trend as the bulk rock lanthanum over ytterbium, and the trend picks up the thinning at this 1170, the initiation of AMCG intrusions, and the thinning at 1060. At this time, the Grenville province underwent a regional extensional tectonics near the end of the Alt1 metamorphic combination, and this extension is recorded by not only the magmatism but also the various structures in this organic belt. Here, I want to note that both methods suffer from sampling bias. With the bulk rock proxy, the sample density is not high, not very high. For example, there's no record during the magmatic layers. And here, this 70-ish kilometer thickness is constrained by only one pluton here. So if you remove this single pluton, then the thickness is somewhere 65 or 60 kilometers, closer to the zircon record. The zircon record is biased towards the felsic magmatism because zircon is more abundant in the felsic magmas, so that the zircon trend shows the thicker across the thickness than the bulk rock lanthanum over ytterbium record in the AMCG emplacement. And both methods are limited to thin magmatic tectonics. So we cannot review the amagmatic plateaus and or pegmatitic late-stage intrusions. And in this panel, we compare the northern origins with the Blue Ridge. The Grenville province versus the Blue Ridge is very similar to Tibet, which is the hinterland, versus Himalaya, which is the orogenic front. They show similar thickness during the orogenic culmination at early Ottoman at around 1080, but the post-glacial thinning in the hinterland is not as evident. The post-glacial thinning is not as evident in the Blue Ridge in the orogenic front. So this is in many ways similar to the relationship between Tibet and Himalaya. Here we compare the evolution of the Grenville Plateau versus the Gandes Arc, which represents the southern Tibet. Okay. The modeled peak crustal thickness during the Grenville orogeny is generally thinner than the Gandes Arc, the Tibet. Okay. The Grenvillian Plateau only transiently reached the crustal thickness of that of the Tibet. Okay. And this repeated thinning is reflected by the abundance of MCG plutons, these mantle-derived magmas, the synclinal extension structures mapped in this area, and possibly magmatism generated by the delamination of the lower crust. All right, then you might ask, we have the petrologic record of these thinning events. Okay, here we only have these geochemical proxies to reveal the first order evolution of this crustal thickness. So we did a field trip here, actually here near Matwa. This is the Alakistan boundary thrust. And according to the mapping by neodymium model age, this Matwa here is a cliff. But in other way, this locality is very close to this Alakistan boundary. Okay. And in the field, these greenish units are mafic gneiss, including retrograde icrogite. In the field, they crop out as lands or pods or dikes intrusion in the massive felsic gneiss. The geochemical discrimination diagram shows that these were largely within plate solite or related to rifting. The mafic gneiss is like this, very massive. There are minor hints of partial melting on this rock. Garnet is very abundant within this greenish matrix. In a more retrogressed version of this rock, the matrix becomes darker, and the garnet is rimmed by a plateau-clay corona, which is a decompression feature. And in more extreme cases, garnet is almost resorbed, and this appears just like a normal amphibolite. The matrix is actually this symplectic intergrowth of clinoperxene and plagioclase. There are also these hornblende that cross-cut these clinoperxene and plateau phase lamellae. Here are these chemical mapping of these symplectites. This is calcium, sodium, manganese, titanium, and magnesium. Note here the CPX has the decreasing sodium towards the plateau place, indicating a potential sodium loss during the decompression, during the formation of symplectites. The plateau place lamellae is like here between oligoclase and Andean. The symplectitic lamellae of Clinopyroxene is largely diopside, but some of these lamellae have already been plotted within this armsite field. And the hornblende, which appears late according to the textual relationship, are traumatite or parasite. If we assume that the decompression of this precursor or the formation of a symplectite was largely isochemical, then we integrate this chemistry, this composition of the symplectite, and this is a perfect on-site composition. So here we have garnet and the on-site precursor. We can say this was an aggregate. The garnet is like this. The rim is somewhat brighter due to the slight enrichment of manganese. Okay, and this is a typical feature of garnet resorption during the retrogradation. The calcium shows a high calcium euhedral shape toward the rim that correspond to this sharp boundary of titanium map. Okay. So we are confident that this part of the garnet was the growth zoning, and the magnesium increases toward the rim. This is smoother than the calcium, so that we infer that magnesium is affected by the diffusion modification more than the calcium. A diffusion of magnesium is faster than calcium garnet. Although this temperature is very high, the garnet still preserves this largely bell-shaped manganese pattern. There is a high manganese core recorded here. So this overall duration of peak metamorphism must have been limited. Then we just calculate the phase diagram to constrain the pressure temperature path. This high calcium peak here corresponds to this pressure temperature condition, which is also recorded in previous studies. And the number 2, which is this high magnesium number peak, the isoplast intersects the calcium here. And this PT condition is consistent with the composition of reintegrated Clinopyroxene. Pressure temperature condition is about 20-21 kilobars at 830 degrees. This prograde heating is recorded by the growth of a garnet here. Okay. During this period, the garnet developed this euhedral growth zoning. This peak condition is also consistent with the record of the zirconium rutile thermometer. Then the titanium in biotite thermometer, as well as the previous studies, record this granulite high amphibolite species retrogression. So largely, there were prograde burial and heating accompanied by partial melting, followed by this near isochemical decompression, and then cooling. There's no OPX in assemblage, so the cooling took place at pressure higher than the OPX stability field. Then this part of the garnet profile developed during the growth donation, garnet growth, so that this diffusion relaxation has to be has to include this time scale of garnet of this excitation decompression, and then we perform the diffusion simulation on garnet profiles on the calcium profile of the garnet, because calcium diffuses the slowest. And on this garnet, this time scale is 35,000 years. On this one is 48,000 years. So about 8 kilobar decompression took place within a time scale of 50,000 years. This leads to an estimate of tens of centimeter per year estimation, which is extremely fast. So here is a very brief conclusion. The retrograde aggregate near Mattawa, Ontario documents the PT path of supersolid isobaric heating to aggregate species conditions, followed by the isothermal decompression. The isothermal decompression was really rapid, and this implies a transient metamorphism decompression within a long-lived hot origin. The fast decompression rate estimated from the short duration indicates rapid excitation to the upper crustal depth, likely in response to the thin collisional crustal thinning in the Grenville origin. Then you might ask, what is the tectonic framework behind this? Recent studies have argued that the dispersion of Columbia or Nuna supercontinent was rather limited, and the Nuna Rodinia together acted as a long-lived stagnant insulator over the atmosphere. The transition from Nuna to Rodinia was not through this complete dispersion and the reassembly. Instead, this transition underwent only a minor rotation and reconfiguration. Okay, so these researchers propose that Nuna and Rodinia was probably a long-lived one supercontinent known as Nuna or Rodinia or Nudinia. Thinner crust might be a result of the hotter mantle, because when the lower crust was heated, it lost the strength. So gravitational collapse during the organic thickening must be frequent. And the magmatism derived from part melting of the upper mantle gave rise to repeated extension and rifting. The hotter mantle enhanced the thermal revolution and destabilized the lower crust, okay, which further gave rise to a delamination, which thins the crust. The thinner crust should have led to a low relief, broad plateau. Okay, when the mantle is hot, the isostatic subsidence of this organic belt also contributes to the low relief. And in reality, there was a major mid-continent rift at about 1.1 billion years ago. So this thin crust might have contributed to the so-called Mesoproterozoic organic presence during the assembly of Nuna and Rodinia. This is a compilation by Cowwood in last year. Here, the orange histogram are the zircon records. Okay. This is assembly of Nuna or Columbia, and this is the assembly of Rodinia. Unlike the other supercontinents, like this Pan-African family of Rodinia, of Gondwana, and this is Himalaya, Tibet, where you see increase in strontium isotope, strontium 87/86 ratio. This is regarded as the contribution of weathered continents, but this upturn of strontium is missing during the assembly of Rodinia. So the weathering flux during this supercontinent amalgamation might be rather limited. And here, this purple curve shows the compelled metamorphic temperature over pressure ratios. Okay. And this assembly of Rodinia and the time before that was featured by this very hot metamorphism. Okay, and then this metamorphic temperature pressure ratio decreases towards in Neoproterozoic and Phanerozoic. And surprisingly, this period of lunar Rodinia corresponds to this low oxygen level in Mesoproterozoic. And this might be due to the limited primary productivity in the ocean, which is further limited by the weathering flux, which carries the nutrients input into the ocean. The Matwa aggregate is here. The peak condition, peak pressure condition is about here, and the granulite overprinting is about here. In a recent paper by Tan et al. 2021, they further calculate the mean elevation of the active continental crust. They see here this assembly of Rodinia, the Grenvillian age, was featured by this very low relief of continental crust. Right, this corresponds to the low strontium ratio, which can be regarded as the low contribution weathering flux from the continent. Right, and this is what they call the orogenic presence. It does not mean that there was no accretion in the plate convergence, but instead there was no mountains, and the Grenville Plateau was probably not an analog of Tibet. It was probably not even a plateau. So this limited weathering flux, shown as this uranium in the shell, molybdenum records in the sedimentary rocks, and the phosphorus concentrations in the rocks, demonstrate that the nutrient input into the ocean was rather limited, and this might have contributed to the so-called boring baleen, this low oxygen level during the Mesoproterozoic. So to sum up, although both bulk rock lanthanum ytterbium ratio and the zirconium European normal proxies could be best, they yield a largely consistent trend of crust thickness of the Grenville origins. The Grenville province underwent repeated episodes of crustal thinning, which prevented it from forming a high Tibet-like plateau in Mesoproterozoic. The Matwa aggregate records the local rapid acclimation, likely in response to one of these thinning events. These thinning events may have been associated with the enhanced atmosphere-lithosphere interactions in response to a warm mantle beneath the long-lived supercontinent. Then the reduced weathering flux from the low orogenic plateaus could have resulted in this stability of biological evolution and ocean atmosphere chemistry during the so-called boring baleen years. Thank you.
Okay, thank you for that talk. And now it's time for questions from our participants. So if you have questions, feel free to open your mic, or you could just type the question in the chat.
or if you have comments.
Okay, I could start a question. I'm curious that for example, for the last point in your conclusions, that reduced weathering flux. So may I know that for this weathering flux, like globally, the controlling factor depends on the, let's say, orogenic plateaus, but does this orogenic plateaus all fall into category like a continent collision? Not really, actually.
Broadly
Right.
speaking, yes. And because this Grenville province was like here, it was just at the core of this Rodinia supercontinent. In many ways, similar to what the role Tibet is playing on modern Earth. So this might dominate the weathering feedback at that time.
Okay. Yeah, because I was thinking that for the circumchemistry to correlate with the thickness of the crust, and for the, like the circumstances provided, either Grenville or Tibet are all coming from the continent collision plateaus. And the overall picture that I want to say is that the global crust thickness. So I was wondering that how these two could be linked to each other. But I do could see the point that the lack of, for example, the lack of plateaus that they cause the reduced weathering flux. I could get that. But for the global average, like say crust thickness, do you have anything to say about that? Or it is not important at all from the perspective of weathering?
So let's just look at Tibet on modern Earth. The Cenozoic cooling, or the global cooling during the Cenozoic, has been regarded as this weathering by the uplift of Himalaya Tibet. And the strontium isotope in seawater is also attributed to the weathering of these evolved continental materials from Tibet Himalaya. So this is where the major rivers on East Asia, South Asia originate from. So it's just clear that these weathering, global weathering, is largely controlled or dominated by these high mountains. Of course, there are exceptions, like during the emplacement, very weatherable materials like large igneous provinces. That is another story.
Okay. The audience participants asked type of questions. The first one from Zoe: what is the cooling rate of the eclogites?
So we don't know actually. We only say here this time scale is this part, but this cooling rate cannot be infinitely fast. So that we just argue that this time scale is the upper limit estimate, and the exhumation rate could be even faster. What is the cooling rate? We don't know, but it cannot be infinitely fast.
Okay. Okay, another question that could you explain the Boothstrap resembling method? A little bit.
That's a good question. I need to refresh my memory by reading the textbook again, but it's not tricky, although I do not know the details at this time. It's actually very straightforward.
Yeah, I could
We
help you
use
with the
Bootstrap just to reduce the scattering, and it's more statistically rigorous.
I have a quick explanation for this. Is that my understanding is that simple way to say is that you have a bag, then I say inside that you have a number of samples. Then in order to increase the number of samples for in order to make the statistics more sounding, then you take one sample out, and then you take this sample also back to the bag, and for the next round of random sampling. So by doing this process, you could increase the number of samples that we have, because the time that when people the situation that when people need to do the bootstrap resampling is that the samples are unbalanced at for example at different interval time period, or the different like say groups of samples that you're interested in. So people need to increase by that. Then you make the number of samples more balanced in each group. So that's why that people need to use this statistical technique. Okay, but you could see more details by Googling, I think. Okay, the next question, I think from Chen Lin. So what's the relationship between the crust thickness variation constraint using zircon euphonium data by Tom in 2021 Science, and the thickness variation of juvenile continental crust by June 2015 using rubidium and cerium ratios?
They are actually two different things. The during 2015 used the rubidium strontium ratios to estimate the thickness of juvenile crust, but in Tang's paper, they don't care where this crust is from. Just this crust might be just a passive carrier of the magma, and we only want to know what the thickness is like for this crust. So the evolution trends of the Tang's paper and the Duin's paper are different, but they are just different things. So there's no surprise that we see two different trends in these papers.
Okay, another question from Yang, and she's asking about the explanation of linking the crustal thickness with the Baccarat composition of LA divided by YB ratio and the euphonium anomaly ratios, zircon ratios. Actually, these two ratios come from two different sources.
Why and how I get the conclusion of the techniques. First of all, why I'm applying these two methods? Because we want to do a benchmark to test whether these two methods are consistent or not. And the other reason is that both methods are somewhat biased, and we just want to see where the discrepancies are from. How do I get the conclusion of crust thickness by calculating? Could you specify your question? Like, what do you expect me to answer? The method or the data interpretation? What's the relationship? So you mean whether they're same, there are discrepancies, and how I.
So what's the okay.
Okay, let me try to answer this. And apologize in advance if I do not answer your question. They are largely consistent. In particular, they both record the major thinning and thickening periods that has been reviewed by the field studies, structural studies. And there are discrepancies because there are sampling bias in both methods. And the equations are just simple, like one is this one, the other one is this one, based on the geochemical ratios. The European anomaly was calibrated against the lesson terbium. So in theory, they should be consistent, but in reality, they're not always consistent. Do I answer your question?
Okay, let's move to the last question. I think it's already in the chat. I think you could read it by yourself and then provide the answer.
All right. The lanthanum ytterbium or strontium yttrium ratio classical thickness relation is derived from modern subduction zones. Yes, it has been suggested that for collisional origins, this relationship needs to be modified. Yes, that is actually the purpose of this study. And also, what's the effect of overall higher temperature in the Proterozoic than the present day on such relationship? All right. So either the lanthanum ytterbium or strontium yttrium or zircon europium anomaly are controlled by the phase relations, by the phase assemblages. Basically, it is the baseness of plateau-clays versus garnet. And this phase relationship is largely insensitive to the temperature. So this hot environment might not compromise the calibrations a lot. And yes, these are calibrated on the basis of modern arcs. The relationship needs to be modified, yes, because in the continental collision zone, it's more complicated than the simple continental arc. And according to a recent paper by Holder et al. 2019, the European anomaly in particular is also affected by the amount of melt, actually. Right, I totally agree with you. This is just a first order approximation, and we hope that with the generation of a large data sets, some of the second order effects could be cancelled out. And actually, this is indeed the motivation of this study.
Okay, I think we ran actually a couple of minutes, more than our schedule. That is great. Also, thank you very much again for giving the talk, Dr. Chu, and thanks everybody for the participation. So next Thursday we will have another seminar. So see you in the you all will see the updated information for that. Thank you again.
Thank you, and thank you for organizing this colloquium seminar.